Hello there, and welcome to Sleepy Science Vault. Settle in. Take a slow, deep breath, and let yourself drift into the quiet, boundless wonder of the universe. We begin, not with a rush, not with noise, but with a simple question. Where are we? Somewhere above you, beyond the ceiling, beyond the clouds, beyond the blue of the sky itself, there is a galaxy. And you, right now, are inside it. The Milky Way, our home in the cosmos, is what scientists call a barred spiral galaxy. Imagine a slow, graceful pinwheel, turning endlessly in the dark. At its center, a long, glowing bar of stars. And from that bar, great spiral arms, reaching outward, like the arms of something ancient, and vast, and calm. This galaxy, our galaxy, stretches somewhere between 100,000 and 150,000 light years across. A light year is the distance light travels in an entire year. And light moves at nearly 300,000 kilometers every single second. Let that settle over you like a warm blanket. 100,000 light years. Not miles. Not kilometers. Light years. And yet, as enormous as this is, much of the galaxy remains invisible to us. Most of the Milky Way's mass is not made of stars, or gas, or dust. It is made of something we cannot see. Something we call dark matter. Dark matter does not glow. It does not shine. It does not reflect light, or emit it, or absorb it. And yet, it is there. We know it is there, because of the way the galaxy moves. You see, when astronomers studied how stars orbit the center of the galaxy, they noticed something unexpected. Stars far out at the edges were moving just as fast as stars closer to the center. That should not happen. Not without something vast and unseen holding it all together. And so we imagine the galaxy wrapped in an enormous, invisible halo. A halo of dark matter, stretching far beyond the visible stars, cradling the whole of the Milky Way in its quiet, invisible embrace. Somewhere within that great spiral, about halfway out from the center, sits a small, ordinary star. Our sun. The sun is not at the heart of the galaxy. It is not at the edge. It rests somewhere in between, in a modest region, making its own slow, patient journey around the Galactic Center. This journey takes a very long time, about 230 million years, for the sun to complete just one full orbit. This span of time has a name: a cosmic year, a galactic year. One long, unhurried loop through the turning dark. And as the sun travels, it does not move in a perfectly flat path. It drifts gently up and then slowly down, above and below the flat plane of the galaxy. A slow, gentle oscillation, like something breathing. the galaxy itself, breathing slowly, in and out, as our sun bobs through it. Over millions and millions of years, the region of the galaxy where our sun resides has a name: the Orion Arm. It is one of the smaller spiral arms of the Milky Way. Not a grand, sweeping major arm, but a quieter spur, a gentler branch. And it is home. And there is something else, something close to us, cosmically speaking, surrounding our solar system. There is an enormous region of very thin, hot gas. Astronomers call it the local bubble, a cavity in the interstellar medium, stretching hundreds of light years across. We do not fully know how it formed. Perhaps ancient stars that exploded long ago carved out this space, left behind a vast, warm emptiness for us to drift through. A quiet pocket in the fabric of the galaxy. And as the solar system moves through the galaxy, it does not always pass through the same surroundings. Over millions of years, we drift through regions of dense gas and regions of near emptiness, through clouds of dust, and through the silence between them. The environment around us is always, slowly, changing. Though on the scale of a human life, it seems perfectly, completely, still. And finally, as we close this first, gentle chapter of our journey, we pull back, far back, past the Milky Way itself. Our galaxy belongs to a group of galaxies, a local group, containing a few dozen galaxies bound together by gravity. And that local group is itself part of something almost incomprehensibly large, a supercluster, a vast, web-like structure of galaxies, stretching across hundreds of millions of light years. It has a name: Laniakea. In Hawaiian, Laniakea means immeasurable heaven. And there you are, resting quietly on a small blue planet, orbiting an ordinary star, in the Orion Arm of the Milky Way galaxy, in the local group, in the immeasurable heaven of Laniakea. You are not lost in the cosmos. You are held by it, nestled within layer upon layer upon layer of something grand and quiet and endlessly, gently turning. Let your body sink a little deeper now. Let your breath slow. We have only just begun our journey, and there is so much more to discover. But for now, simply rest in the knowledge of where you are. Safe, still, and wonderfully, impossibly small, in the most beautiful way imaginable. And so, we drift a little deeper. The breath slows, the body settles, and we allow ourselves to travel, not just through space, but through time. Because the Milky Way you are resting beneath tonight was not always as it is now. It was not born complete. It was not placed here, whole and perfect, in a single moment. It was built, slowly, patiently, over an almost unimaginable span of time. Piece by piece. Merger by merger. Over more than 12 billion years. 12 billion years. The universe itself is only about 13.8 billion years old. That means our galaxy began forming when the cosmos was still very young, still finding its shape, still learning what it wanted to be. In those earliest eons, small clumps of gas and dark matter began to find each other in the dark, drawn together by gravity, slowly, gently, inexorably, merging, growing. What began as scattered fragments gradually became something larger, and then larger still. This process did not happen quickly. There was no sudden moment of completion. The Milky Way has been assembling itself for nearly as long as time has existed, and in some ways, it is still assembling itself, even now. Every time a smaller galaxy wandered too close, gravity reached out and drew it in, slowly pulling it apart, stretching it into long, trailing ribbons of stars. And those ribbons, those streams of ancient suns, still exist today. Astronomers call them stellar streams, and they are one of the most beautiful things in all of astronomy. Imagine the ghost of a galaxy that no longer exists as it once was, leaving behind only a long, curving trail of stars. A fossil, a memory, written not in stone, but in starlight. These streams wrap around the Milky Way, tracing the paths of ancient galaxies that were pulled apart and absorbed long, long ago. They are quiet echoes of collisions that happened billions of years before the Earth even existed, before our sun had ignited, before any of this was here. One of the most significant of these ancient mergers happened roughly 8 to 10 billion years ago. A large dwarf galaxy came too close to the young Milky Way, and it did not survive the encounter. Astronomers have given this lost galaxy a name: Enceladus, sometimes called the sausage merger, because of the elongated shape its stellar debris traces through the heart of our galaxy. The stars from this ancient collision did not simply vanish. They are still here, scattered through the inner halo of the Milky Way, moving in stretched, looping orbits that betray their foreign origin. Stars that were born somewhere else, in another galaxy entirely. And yet here they are, woven into the fabric of our own. Some of the stars absorbed from ancient mergers do something particularly striking. They orbit backwards, while the vast majority of stars in the Milky Way's disk travel in the same grand, sweeping direction. Some stars move against the flow, orbiting in the opposite direction to the rotation of the galaxy itself. These retrograde stars are like travelers moving the wrong way on a vast, cosmic road. Their unusual paths are a whisper of their origins, a sign that they came from somewhere else, from a galaxy that collided with ours, from a different angle, long before the Earth was born, and scattered across the outer reaches of the Milky Way. In the vast, dim halo that surrounds the disk, there are tiny galaxies, so small, so faint. They were only discovered in recent decades. We call them ultra-faint dwarf galaxies. Some of these tiny companions contain only a few hundred or a few thousand stars. Compare that to the Milky Way's several hundred billion, and you begin to understand just how small they are. They are whispers of galaxies, suggestions of galaxies, barely there at all, and yet there, orbiting our galaxy like quiet, dim satellites in the cold dark of intergalactic space. And here is something remarkable about these tiny galaxies. Despite their small number of stars, they contain enormous amounts of dark matter. In fact, some of these ultra-faint dwarfs are among the most dark matter-dominated objects known to science. The ratio of dark matter to normal matter in these galaxies can be hundreds, or even thousands, to 1. For every particle of gas or star you can see, there are hundreds of times more dark matter, holding it all together. Invisible, silent, vast. It is humbling, somehow. These tiny, faint, barely visible collections of stars, surrounded by invisible halos, so much larger than themselves, resting in the dark, held together by something we cannot see. Now, let your mind drift gently to another kind of ancient structure, floating through the halo of the Milky Way, are objects called globular clusters. A globular cluster is a tightly packed ball of stars. Thousands, sometimes hundreds of thousands of stars, bound together by gravity, into a dense, glowing sphere. They are extraordinarily old. Some of the oldest objects in the entire universe. The ancient globular clusters that orbit the Milky Way, formed in the earliest chapters of cosmic history, before the galaxy's disk had fully taken shape, before most of the galaxy's stars had even been born. They are artifacts, living fossils of the early universe, still orbiting, still glowing. After more than 12 billion years, when astronomers study globular clusters, they are looking back in time, reading the earliest pages of the Milky Way's long, long story. And there is another ancient structure, closer to home, beneath the thin, flat disk of the galaxy, where our sun and most of the familiar stars reside. There is an older, thicker layer. Astronomers call it the thick disk. The thick disk formed very early in the Milky Way's history. It is made of older stars. Stars that formed when the galaxy was still turbulent, still finding its shape. Stars that have been quietly orbiting for 8, 9, 10 billion years or more. Over time, the galaxy settled. The turbulence calmed, and a thinner, flatter disk formed within the thick one. The disk where most of the galaxy's activity happens today. Where new stars are still being born. Where spiral arms still sweep through clouds of gas and dust. But beneath it all, the thick disk endures. Old. Patient. Still. Out in the halo of the galaxy. Among the ancient stars and globular clusters, astronomers have found something extraordinary. Stars so old that they contain almost no metals. In astronomy, the word metal has a special meaning. It refers to any element heavier than hydrogen and helium, carbon, oxygen, iron, gold. All of these are metals to an astronomer. The very first stars in the universe formed from almost pure hydrogen and helium, because heavier elements had not yet been created. Those heavier elements, those metals, were forged later, inside stars, and scattered across space when those stars exploded. So a star with very few metals is a very old star, one that formed before the universe had been, enriched by many generations of stellar death and rebirth. These extremely metal-poor stars in the halo are among the oldest stars we have ever found. Some may have formed within the first few 100 million years. After the Big Bang itself, they are not just old stars. They are witnesses, ancient observers, who have been quietly burning since nearly the beginning of everything. And some of these ancient stars carry within them a remarkable kind of chemical signature. The elements inside them were not built up gradually by many generations of supernovae. They were enriched by only a handful, perhaps just one or two, or a few, massive stellar explosions, long before the galaxy had filled with the ordinary chemistry of later stars. Think of that for a moment. A star whose entire chemical composition was shaped by just one or two explosions, billions of years ago. Everything it contains, every atom in its depths, came from a specific, singular event. A moment of tremendous violence that wrote its signature into the quiet fabric of a star that has been burning ever since. This is how the galaxy was built. Not all at once. Not cleanly. Not simply. But through collision and merger. Through the slow pull of gravity. Through explosions and streams in ancient clusters. And the quiet persistence of stars. So old they remember a universe we can barely imagine. The Milky Way you rest beneath tonight carries all of this history within it. Every star you have ever seen in the night sky is part of a story that began more than 12 billion years ago. And that story is still being written, still unfolding, still turning, slowly, in the dark. Let that thought carry you, like a current beneath still water. You do not need to hold on to it. Just let it move beneath you. As your breath slows, and your body grows heavy. And the long, ancient story of the galaxy drifts quietly through your mind. We are only just beginning, and there is so much more still ahead. But for now, simply rest, and still, we drift. The breath continues its slow, quiet rhythm. In and out. There is no hurry here. No destination we must rush toward. Only the gentle unfolding of one wonder after another. We have traveled through the formation of the galaxy, through ancient mergers and stellar streams, through fossils of long-gone galaxies, and stars so old they remember the earliest universe. Now, we go a little deeper, a little quieter, into the chemistry of stars themselves, and then into the grand architecture of the galaxy's own remarkable structure. You may not think of stars as carrying history within them, but they do. Every star is a kind of archive, a record of everything the universe had already created by the time that star was born. Some stars carry within them unusual and striking chemical fingerprints. Astronomers call them chemically peculiar stars. And they are exactly what they sound like. Stars whose compositions are strange, unexpected, different from what the surrounding region of the galaxy would suggest. These stars preserve, in their very atoms, the memory of specific, ancient events. A nearby supernova that went off just before they formed. A collision between two neutron stars that scattered rare elements across a patch of gas. Moments before that gas collapsed into new suns. The elements locked inside these stars have not changed since the stars were born. They are a chemical photograph, frozen in time. A quiet record of something violent and extraordinary that happened billions of years ago. And when astronomers read these chemical fingerprints carefully, they find that stars across the galaxy can be sorted into broad families. Two great populations with different chemical stories to tell. One group of stars is rich in what astronomers call alpha elements. Elements like oxygen, magnesium, silicon, calcium. These elements are produced quickly by massive stars that live fast and die in tremendous explosions. Stars that burned out long before our sun was born. The high alpha stars are generally older. They formed early in the galaxy's history, when massive, short-lived stars were exploding frequently, enriching the surrounding gas with these elements very rapidly. The other group, the low alpha stars, formed later, after the galaxy had settled somewhat, after a different kind of stellar death had time to contribute. Slower explosions, called Type Ia supernovae, which produce large amounts of iron, but fewer of those alpha elements. So the ratio of alpha elements to iron in a star is like a timestamp, a way of reading roughly when that star was born. High alpha older, formed in the galaxy's more turbulent youth. Low alpha, younger, formed in calmer, later times. It is a beautiful thing to contemplate, that by measuring the chemistry of a single star, astronomers can place it somewhere on the long timeline of galactic history. Each star carrying its own quiet birth certificate, written in the language of elements. And there is another pattern, written across the face of the entire galaxy, not just within individual stars, but across vast distances. Stars closer to the center of the Milky Way tend to be richer in metals, more iron, more of the heavier elements, more chemical complexity. Stars farther out, toward the edges of the disk, tend to be poorer in metals, simpler, more ancient in their chemistry, less enriched by the generations of stellar death that have been churning away near the Galactic Center for billions of years. This pattern, this gradual change in chemical richness across the face of the galaxy, is called a radial metallicity gradient. Radial, meaning it changes with distance from the center. Metallicity, meaning the richness of heavier elements. Gradient, meaning it changes smoothly, gradually, across space. Imagine the galaxy as something like a very old tree. The rings closest to the center, dense, rich, full of history. The outer rings, thinner, quieter, less layered with time. The center of the Milky Way has been the most active region for the longest period of time. Stars have been forming and dying there for billions of years. Each generation, leaving behind a little more chemical complexity, a little more richness, a little more of the heavier elements that make planets and oceans and living things possible. But the story is not perfectly smooth. Nature rarely is. As astronomers have mapped the chemical composition of stars across the disk of the Milky Way, they have found something unexpected. At certain distances from the center, the metallicity does not simply continue to decline gradually. It drops suddenly, noticeably. These are called metallicity breaks, places in the disk where the chemical gradient changes abruptly, where the expected smooth pattern is interrupted. What causes these sudden breaks? Astronomers are still working to fully understand them. Perhaps they mark the edges of different structural regions of the galaxy. Perhaps they are the echoes of ancient mergers, where material from outside the galaxy was stirred into the disk, disrupting the smooth chemical flow. Or perhaps they mark the influence of the galaxy's great spiral arms, which can change how gas moves and where stars form, in ways that leave chemical footprints across vast stretches of space. We do not yet know for certain, and there is something deeply peaceful about that. The galaxy holds its mysteries gently, revealing them slowly to those patient enough to look. And now, let us pull back a little. Let us look at the galaxy itself. not just its chemistry, but its shape, its grand, sweeping architecture, the magnificent structure that holds all of these stars and mysteries together. At the very heart of the Milky Way, there is no simple point, no single glowing center, and nothing more. Instead, there is a bar, a long, dense structure of stars, stretching across the inner galaxy, thousands of light years in length, slowly, steadily, rotating. This bar is not merely decorative. It does something important. As it rotates through the inner galaxy, it acts almost like a great cosmic plow. Its gravity, pushing and pulling on the gas around it, driving streams of gas inward, funneling material toward the galactic center. This inward flow of gas feeds the regions near the center of the galaxy. It fuels star formation there. It feeds the processes around the enormous black hole that sits at the very heart of the Milky Way. The bar is not just a structure. It is an engine, a slow, turning mechanism at the core of our galaxy, quietly, relentlessly, doing its work. And here is something subtle and wonderful. The bar does not rotate at the same speed as the spiral arms that extend from it. The bar has its own rotation rate. The spiral arms have theirs. These are different. They do not turn together, as if the galaxy were a rigid, solid object. The galaxy is not rigid. It is fluid, dynamic. Different parts of it, moving at different speeds. Different structures, following different rhythms. A vast, complex, slowly turning system of many overlapping motions. And the spiral arms themselves are stranger than they might first appear. You might imagine that a spiral arm is simply a fixed collection of stars, a permanent feature of the galaxy, like the arms of a pinwheel, always containing the same material. But this is not quite right. The spiral arms of the Milky Way are density waves. Think of a slow-moving traffic jam on a long, quiet road. The jam itself moves slowly or barely at all. But individual cars are constantly entering the jam from behind, passing through it, and emerging from the front. The jam is a pattern, not a fixed collection of vehicles. The vehicles pass through it. The spiral arms work in a similar way. Stars and gas drift into the arm. They slow slightly as they pass through the region of higher density. They spend more time there, which is why the arm appears bright and full. And then they drift out the other side. The arm is a wave, a slow, sweeping pattern, moving through the stars of the galaxy. The stars themselves are not permanently part of it. They merely pass through, like travelers moving through a crowded place, and then continuing on their way. Our own sun has passed through spiral arms many times over its long life, each passage taking millions of years. Each passage subtly changing the environment around us. And there is one more thing worth knowing about these great arms. They are not perfectly symmetrical. They are not mirror images of each other. The spiral arms of the Milky Way are asymmetric. Different arms have different lengths, different brightnesses, different amounts of gas and star formation happening within them. The galaxy, for all its grandeur, is slightly lopsided, slightly irregular. Like most beautiful things in nature, it does not follow a perfectly rigid plan. And finally, there is a concept that ties much of this together. A concept called corotation. As the density wave of a spiral arm sweeps through the galaxy, there is a particular distance from the center, where the speed of the wave matches the speed of the stars orbiting in the disk. At this distance, stars in the spiral pattern rotate together, in sync, neither overtaking the other. This region is called the corotation zone. And near corotation, and at other specific distances from the center, the gravitational rhythms of the galaxy create what astronomers call resonances, places where the orbital periods of stars fall into simple, repeating ratios with the rotation of the spiral pattern. These resonances shape the galaxy. They influence where gas piles up and where star formation happens. They help define the edges of structural regions. They are the quiet, mathematical heartbeat of the Milky Way's grand, rotating architecture. Rhythms within rhythms, patterns within patterns. The galaxy, endlessly, gently, organizing itself according to the deep laws of gravity and motion. And here you are, resting, breathing slowly, part of all of it. Your atoms were forged in ancient stars. Your planet orbits a sun that passes through density waves on its long journey around a barred spiral galaxy, wrapped in invisible dark matter, turning through the immeasurable heaven of a supercluster. You are not separate from any of this. You are woven into it, quietly, completely. Let your eyes grow heavy now. Let the great turning of the galaxy become the rhythm beneath your rest. Slow and vast and endlessly, gently moving. There is more to discover, much more, but it will wait for you. It has been waiting for billions of years. A little longer is nothing at all. Rest now. We continue whenever you are ready. And so, we rest a moment longer in the stillness. The breath moves slowly, in and out. There is nothing to do, nowhere to be. Only this. Only the quiet and the vast, turning darkness, full of wonders. We have learned something of the galaxy's chemistry, something of its great rotating structure, its bar, its density waves, its resonances. And now, we go deeper into the architecture itself, into the subtle, surprising ways. The Milky Way bends, and ripples, and breathes. We begin with something delicate, something almost musical. Just as the spiral arms create regions of density, that shape where stars form and where they don't, there are places in the galaxy's disk where these gravitational rhythms create something even more structured. Rings and gaps at certain distances from the Galactic Center. The resonances we spoke of. Those places where orbital rhythms fall into step with the spiral pattern. Cause material to pile up. Gas and dust accumulating in slow, sweeping rings. Faint traces of order written across the face of the galaxy. And between these rings, there are gaps. Regions slightly emptied of gas. Slightly quieter. Slightly less active. It is reminiscent of the rings of Saturn, where the gravitational influence of moons creates gaps and structures in the surrounding material. The same principle, but written across a canvas, billions of times larger. Gravity, endlessly sculpting, endlessly organizing, even across distances so vast, the mind can barely hold them. Now, imagine looking at the Milky Way from far above, from some impossible vantage point, beyond the galaxy itself. You might expect to see a flat, perfect disk, a neat spiral, lying smooth and even, like a coin resting on a table. But this is not quite what you would find. The disk of the Milky Way is warped. Not dramatically, not violently, but unmistakably. The outer regions of the disk curve upward on one side and downward on the other, like the brim of a very wide, very gently bent hat. And this warp is not perfectly still. It wobbles. Slowly, imperceptibly slowly. The warp disk precesses, rotates around its own axis of distortion, like a coin that has been spun on a table, and is just beginning, very slowly, to tip. What caused this warp? The most likely answer is the pull of the Milky Way's satellite galaxies. The large and small Magellanic Clouds, those two companion galaxies, orbiting far beyond the main disk, exert a gentle, persistent gravitational tug on the outer edges of our galaxy. Over billions of years, that tug has bent the disk, pulled it slightly out of true. And there is more. The disk does not only warp, it ripples, spreading outward across the disk of the Milky Way, like the surface of a pond, after something heavy has fallen into it. There are ripples, vast, slow, barely perceptible waves, moving through the stars and gas of the disk. These ripples are echoes, memories of ancient collisions, when a satellite galaxy, or a large clump of dark matter, passed through or near the disk. Long ago, it sent waves outward, waves that have been slowly spreading ever since. We are still feeling those waves today. The galaxy around us is still ringing from impacts that happened billions of years ago. A bell struck long in the past, still faintly sounding. And as we move outward, toward the very edges of the galaxy's disk, the orderly structure begins to soften, to fray. The outer disk becomes irregular, warped not just gently, but more dramatically, twisted, flared. The neat, flat spiral, giving way to something looser and less defined. Out here, at the galaxy's edges, the influence of the central mass is weaker. Gravity's organizing hand does not reach quite so firmly, and the disk reflects that, growing thicker, more ragged, more easily disturbed by the pull of outside forces. The edge of the galaxy is not a clean boundary. It is a gradual fading, a slow dissolving of structure into the open dark. Now let us return toward the center, toward the heart of the Milky Way. At the center of the galaxy, there is a large, dense region of old stars. We call it the bulge. You might imagine it as a smooth, rounded sphere, a glowing ball of ancient stars, nestled at the center of the spiral arms. But again, the galaxy is more surprising than our expectations. The bulge of the Milky Way is not round. It is boxy. When astronomers look at the distribution of stars in the bulge, they see something shaped less like a sphere and more like a rectangle, or, seen from a certain angle, like a peanut. Two lobes, bulging outward above and below the plane, connected at the center. A peanut, made of billions of ancient stars. This boxy, peanut-shaped structure is thought to be the result of the bar. As the bar at the center of the galaxy rotates over billions of years, it becomes unstable in the vertical direction. Stars begin to oscillate up and down in patterns called banana orbits. And over time, these oscillating orbits collectively give the bulge its boxy, rounded shape. It is a remarkable thing. The gentle, persistent interplay of gravity and motion, sculpting billions of stars into a shape that looks almost intentional, almost designed. And above and below the flat disk, the galaxy does not simply end. It fades gradually as you move away from the midplane of the galaxy, upward or downward into the halo. The density of stars changes. The kinds of stars change. The chemistry of stars changes. These are called vertical gradients, and they tell a story of how the galaxy has evolved. Close to the plane, younger stars, more metals, more recent star formation. Higher above or below, older stars, less metals, more ancient origins. The galaxy is layered, like geological strata in a cliff face. Each layer, a different chapter of history. Each layer, a different era of the Milky Way's long life. And all of this, all these stars and layers and structures, are in motion. Constant, complex, beautiful motion. The rotation speed of stars across the disk is not uniform. It varies. In the inner galaxy, near the bar and bulge, rotation speeds change rapidly with distance. Farther out, in the main disk, the rotation curve flattens. Stars at very different distances from the center orbit at surprisingly similar speeds. This is one of the clearest signs of dark matter. The invisible halo providing the extra gravity needed to keep those outer stars moving so fast. And within this overall rotation, there are additional motions. Subtle, complex, overlapping. Astronomers call them streaming motions. Large-scale flows of stars and gas that deviate slightly from simple circular orbits. Near the spiral arms, gas flows inward on one side of the arm and outward on the other. Near the bar, gas streams along its length, then curves inward toward the center. The galaxy is not just rotating. It is breathing, flowing, moving in ways that are layered and intricate, and still not fully mapped. Even on smaller scales, the orderly motion of stars is interrupted. Here and there across the disk, concentrations of mass pull slightly on passing stars. Dense molecular clouds, stellar clusters, remnants of ancient mergers, each one exerting its own small gravitational nudge, perturbing the paths of nearby stars, ever so slightly, bending trajectories by tiny fractions that accumulate over millions of years into something noticeable. No star travels a perfectly smooth path. Every orbit is slightly irregular, slightly influenced by the mass of everything around it. The galaxy is not a machine of perfect, frictionless precision. It is messy, alive with interaction, endlessly nudging itself into new configurations. And now, something shifts. We have been studying the galaxy from the outside, mapping it, measuring it, understanding its shape and motion. But now, we begin to travel. Imagine yourself lifting gently away from where you rest. Not with any urgency, not quickly, simply rising, drifting, moving outward through the darkness, and then forward into the galaxy itself. The first thing you encounter as you begin your journey through the spiral arms is light. Not the steady, ancient light of old stars, but something younger, something brighter, something alive with the process of creation. The spiral arms of the Milky Way are not just rivers of stars. They are rivers of gas and dust and possibility. Woven through the arms are vast clouds of gas and dust, some cold, some warm, some collapsing inward under their own gravity, slowly, inexorably, becoming something new. These clouds, and the glowing regions around them, are called nebulae. Some nebulae glow, illuminated by the fierce, hot light of young stars, newly born within them. The gas around a young, massive star absorbs that ultraviolet light and re-emits it as color, as soft, luminous clouds of red, and pink, and violet. These glowing clouds are called emission nebulae, and they are among the most beautiful objects in all of the known universe. The Orion Nebula, the Eagle Nebula, the Carina Nebula, names that carry within them a sense of wonder that no description can quite capture. Within these glowing clouds, stars are being born right now, at this very moment. As you rest, and breathe, and drift towards sleep, somewhere in the spiral arms of the Milky Way, a cloud of gas is collapsing. A new star is igniting for the first time. A sun that has never shone before is beginning to shine. The spiral arms are not just structures. They are nurseries, places where the galaxy makes new suns, new worlds, new possibilities, and we are about to travel through them. Slowly, gently, with all the time in the universe. Let the image settle over you now. A journey through glowing clouds of color, through the soft light of newborn stars, through the quiet, vast, creative heart of a spiral arm. There is no hurry. The nebulae have been glowing for millions of years. They will glow for millions more. They are waiting, softly luminous, patient as starlight. And so are we. Breathe slowly now. Feel the weight of your body sinking gently into stillness. The journey has begun, and it is beautiful. Rest. We continue whenever you are ready. And still, we travel, drifting through the soft glow of the spiral arms. There is no sound out here. No wind. No rush of movement. Only the slow, quiet unfolding of one vast wonder after another. The galaxy around us is not sleeping. Even now, as you rest. Even now, as your breath slows, and the world grows quiet around you. The Milky Way is alive, creating, burning, building, doing what it has done for 12 billion years, making stars. Right now, somewhere in the spiral arms we are drifting through, new suns are being born. The Milky Way, today, in this very era of cosmic history, is still actively forming stars. Not as rapidly as it once did. In its youth, the galaxy was a much more vigorous place. Star formation raged across the disk, at rates far higher than today. But the process has not stopped. It has only slowed, settled into something more measured, more patient. Today, the Milky Way forms perhaps a few new stars. Every year, a handful of new suns added to the galaxy's vast family. Each time the Earth completes another orbit. Quiet, steady, ongoing. The galaxy, still at work, still building itself, one star at a time. And as we drift through the spiral arms, we notice something. The arms are not all alike. Each of the Milky Way's great spiral arms has its own character, its own history, its own population of stars and planetary systems. Some arms are richer in older stars. Some contain more recent star formation. Some regions within the arms host planetary systems very different from our own. Different in age, different in chemistry, different in the kinds of worlds they contain. Think of the spiral arms as different neighborhoods within the same vast city, each with its own atmosphere, its own architecture, its own story. And just as cities have older districts and newer ones, the disk of the Milky Way has regions where the stars skew older and regions where they skew younger. This is called an age gradient. Closer to the center of the galaxy, the stellar populations tend to be older on average. The inner regions formed their stars early and have been living with those stars ever since. Farther out, toward the edges of the disk, the stars tend to be somewhat younger. Star formation in the outer disk has continued more recently, and in some places is still vigorous today. The galaxy grows younger, in a sense, as you move outward through it. A subtle gradient of age, written across hundreds of thousands of light years. But within this general pattern, there are exceptions. Bright, dramatic, impossible to ignore. Scattered across the spiral arms are regions where star formation is not slow and steady, where it is not a handful of new stars per year. In these places, star formation is explosive. These are called starburst regions. Vast amounts of gas falling together, compressing, triggering wave after wave of new star formation. Hundreds, sometimes thousands of new stars, igniting in a relatively small region of space, in a cosmically brief period of time. Starburst regions blaze. They outshine entire ordinary stretches of galaxy. They are the brightest, most productive places the spiral arms have to offer. And they do not last. The very stars they create begin to undo them. When a massive star is born, it does not simply sit quietly and shine. It pushes. The most massive young stars pour out tremendous quantities of ultraviolet radiation. They drive powerful stellar winds, streams of particles rushing outward at millions of kilometers per hour. And these winds carve into the surrounding gas, pushing it outward, compressing it into thin, glowing shells, hollowing out enormous cavities in the very clouds that gave birth to the stars. These cavities are called bubbles. A single massive young star can carve a bubble tens of light years across. A cluster of massive stars can hollow out a region hundreds of light years wide. The gas is pushed to the edges, piled up into dense, glowing walls, and sometimes that compressed gas is squeezed just enough to begin collapsing under its own gravity, to trigger yet more star formation. Along the walls of the bubble, stars creating the conditions for more stars. A chain of creation, spreading outward through the gas, like ripples from a stone dropped in still water. It is a cycle, endlessly repeating, endlessly renewing. And as we drift through these regions of creation, we notice smaller structures, delicate ones, easy to overlook if you are moving too quickly. But we are not moving quickly, branching off from the main spiral arms, like smaller streams flowing away from a great river, are structures astronomers call spurs and feathers. These are smaller concentrations of gas in young stars, wisps of star formation, extending outward from the main arms, curving gently into the spaces between. Many of the young star clusters in our own part of the galaxy do not sit neatly inside a spiral arm. They float in these spurs and feathers, slightly apart from the main structure. Quiet groupings of young suns, drifting in the interarm regions. Our own solar system sits in one such region, the Orion Arm, where we reside, is itself considered a spur, a feather, a smaller offshoot of the larger spiral structure. We are not in a grand, sweeping arm. We are in something quieter, a smaller thread of the galaxy's great tapestry, and nearer to the center of the galaxy. The character of star formation changes, becomes more intense, more concentrated. Close to the Galactic Center, there are regions of extraordinary stellar density, places where massive, young star clusters have formed in the turbulent, gas-rich environment near the heart of the Milky Way. These are not modest clusters. They are enormous, containing hundreds of thousands of stars, packed into regions just a few light years across. Some of the most massive stars known to exist anywhere in the galaxy are found in these clusters near the center. Stars tens, even hundreds of times more massive than our Sun, burning so fiercely they will exhaust their fuel in only a few million years. Brief, blazing lives. In cosmic terms, the Galactic Center is a place of extremes, of intensity and turbulence. That makes our quiet corner of the Orion Arm feel very peaceful indeed. And yet, for all the variety we have seen, all the differences between arms and regions and ages, there is something surprisingly consistent about the Milky Way's stellar population. When astronomers measure the distribution of stellar masses across different parts of the galaxy, they find something remarkable. The proportion of massive stars to smaller stars, the ratio of giants to dwarfs, is roughly similar across many different regions. It is called the initial mass function, and it appears to hold across vast stretches of the galaxy. When a cloud of gas collapses to form stars, it tends to produce a similar mix. Many small, dim, long-lived stars, fewer medium-sized ones like our Sun, and only a handful of the great, blazing giants. This consistency is surprising. You might expect different environments to produce very different populations, but nature seems to follow a similar recipe. Again and again, across arms and ages and regions, the galaxy makes its stars in a remarkably steady proportion, a kind of cosmic democracy. The same mix of large and small, wherever new stars are born, and the raw material for all of this creation, for all these stars being born across the arms, comes from structures almost too large to imagine. Scattered through the spiral arms are the great reservoirs of the galaxy, the places where star formation ultimately begins. They are called giant molecular clouds. These are not thin wisps of gas. They are vast, some of the largest structures in the galaxy that are not made of stars. A single giant molecular cloud can contain hundreds of thousands, or even millions of times the mass of our Sun, all of it in gas and dust. Cold, dark, dense, slowly drifting through the spiral arms. Inside these clouds, the gas is shielded from the harsh radiation of nearby stars. It can cool. It can condense. Molecules can form. Complex molecules. In the cold, sheltered interior. And when conditions are right, when a density wave passes through, or a nearby supernova sends a shock wave, or simply when enough mass is gathered, the cloud begins to collapse. Fragments of it, contracting, heating as they fall inward, until the core grows hot enough to ignite, to fuse hydrogen, to become a star. A giant molecular cloud is both a nursery and a waiting room, a place of vast, cold potential, on the edge of becoming something brilliant. And connecting these great clouds, threading through the spiral arms, are structures even larger, even more subtle. Astronomers have discovered enormous filaments of cold gas stretching across the galaxy, hundreds of light years long, sometimes longer. These cold gas filaments are like the rivers and highways of the interstellar medium, channels through which gas flows, slowly, over millions of years, toward the denser regions where stars will form. Some filaments feed directly into giant molecular clouds, slowly supplying them with fresh material, sustaining them, keeping alive the reservoirs from which future stars will be born. Others simply drift, long, thin, cold threads of gas, crossing the spaces between the arms, quiet, barely visible, carrying within them the seeds of suns not yet born. These filaments are among the largest coherent structures in the galaxy, and yet they are cold and dark and very nearly invisible. It is a beautiful paradox. The structures that will eventually produce the brightest, most blazing objects in the galaxy are themselves among the coldest and darkest things within it. Creation, beginning in darkness, in cold, in stillness, rather like the quiet you are resting in right now. A stillness full of potential, a darkness full of things not yet begun. Let that thought drift through you, like a wisp of cold gas, moving slowly through the space between the stars. You are resting, and the galaxy is creating. And both of these things are happening at exactly the right pace, exactly as they should. Breathe slowly. Sink a little deeper. The stars are still being born. The filaments are still flowing. The giant clouds are still waiting for the right moment to collapse into light. And you are drifting gently, peacefully, through the quiet, creative heart of a spiral arm. Rest now. The journey continues. Whenever you are ready, and we drift still deeper. The breath is slow now, easy. There is no effort here, no weight to carry, only the gentle, unhurried movement through the arms of a living galaxy. We have passed through nurseries of stars, through glowing nebulae and cold, dark filaments, through bubbles carved by blazing young suns and quiet spurs, drifting between the great arms. And now, we slow even further. We turn our attention to something smaller, something almost invisible, and yet, something absolutely essential. Inside the giant molecular clouds, in the coldest, darkest, most sheltered regions, something extraordinary is happening. Chemistry. Not the chemistry of stars or explosions, but quiet chemistry. Patient chemistry. The slow, cold joining of atoms into something more complex. Inside these clouds, astronomers have detected molecules. Not simple ones. Not just hydrogen and helium, but organic molecules. Molecules containing carbon. Molecules that, on Earth, we associate with life itself. Formaldehyde, methanol, ethanol, glycine, an amino acid, one of the building blocks of proteins. These molecules form on the surfaces of dust grains, deep inside the cold clouds, where there is almost no light, almost no energy. And yet, somehow, atoms find each other, bond, become something new. The interstellar medium is not empty. It is not sterile. It is a vast, cold, slow-moving chemical laboratory. And the dust grains themselves are remarkable things. In the coldest parts of the molecular clouds, dust grains become coated in ice. Not liquid water, but thin mantles of frozen molecules. Water ice, carbon dioxide ice, ammonia ice. These icy coatings act as surfaces where chemistry can happen, where molecules can meet and react and combine into something more complex. When a nearby star eventually ignites and warms the surrounding cloud, these ices can evaporate, releasing their molecules into the gas, flooding the young stellar system with organic chemistry. It is thought that icy dust grains may have seeded the early Earth with some of the organic molecules needed for life to begin. The chemistry of life may have started not on Earth, but in the cold, dark heart of a molecular cloud, long before our sun had lit, long before our planet existed, drifting, waiting, patient, in the quiet dark between the stars. And the space between the stars is not one simple thing. It is many things. Astronomers speak of the interstellar medium, the material that fills the spaces between stellar systems. And it is not uniform. It is layered, complex, full of contrast. There are regions of cold, dense molecular gas, the clouds we have been drifting through, dark and quiet and thick with potential. There are regions of warm, neutral hydrogen gas, spread more thinly across the disk, filling the spaces between the clouds. There are regions of warm, ionized gas, heated and lit by nearby stars, glowing softly. And there are regions of extremely hot gas, thin almost beyond imagining, heated to millions of degrees by the shock waves of supernovae. All of these coexist in the galaxy. Different temperatures, different densities, different characters, overlapping and interacting in ways that are still not fully understood. The interstellar medium is not a background. It is not simply the space between the interesting things. It is one of the interesting things. A complex, dynamic, multi-layered environment through which everything else moves. And sometimes, the supernovae that heat portions of this medium do not act alone. When many massive stars form together in a cluster, they live fast and die together, one after another, exploding in great supernovae. Over the course of a few million years, Each explosion sends a shockwave outward, and these shockwaves combine, merge into something larger, something far more powerful than any single supernova could produce. A superbubble, an enormous cavity, blown into the interstellar medium by the combined force of many stellar deaths. Superbubbles can grow to be hundreds of light years across, sometimes larger, sweeping up gas into thick, glowing shells, heating the interior to extreme temperatures, creating vast, hot voids in the fabric of the galaxy's gas. The local bubble, the region our own solar system drifts through, is thought to be one such superbubble, carved out long ago by supernovae that have since faded, leaving behind only this warm, thin cavity that we have been sailing through for millions of years. We live inside the remnant of ancient stellar deaths, inside a bubble blown by stars that no longer exist. There is something strangely peaceful about that. And even larger than superbubbles are structures called giant HI supershells. HI, pronounced H1, refers to neutral hydrogen gas, the most abundant gas in the galaxy. A giant HI supershell is an enormous expanding shell of this neutral hydrogen, pushed outward by tremendous energy releases within the galaxy. Supernovae, stellar winds, perhaps even the energy of star-forming regions, working together over long periods. These supershells can grow to be thousands of light years across, among the largest discrete structures in the entire galaxy, slowly expanding, pushing the interstellar medium outward before them, like the surface of a vast, invisible balloon, inflating in imperceptible slow motion. And there is one more force shaping the material of the galaxy, one that works not through explosions, but through the simple, quiet geometry of rotation. The galaxy does not rotate as a rigid body. Different parts of it orbit at different speeds. And this difference in speed means that any extended structure, any group of stars or cloud of gas that stretches across different orbital radii will be slowly pulled apart, stretched, sheared. This is called galactic shear. A young cluster of stars, born together in the same cloud, will over time be pulled gently apart by the difference in orbital speed between its inner and outer members. The inner stars orbit a little faster, the outer stars a little slower, and gradually the cluster is stretched into a long, curving stream of stars. This is one reason why open star clusters, those loose, young groupings of stars born together, do not last forever. Over hundreds of millions of years, galactic shear slowly dissolves them, spreads their stars across the arm, until they are no longer a cluster at all, just individual stars, scattered along an orbit, carrying only their shared chemistry as a memory of being born together. The galaxy is patient. It unravels things slowly and gently. And now, something shifts in our journey. We have been drifting through the galaxy, imagining what we might find there, what the clouds contain, what the gas looks like, what forces shape the spaces between the stars. But now, let us consider something different, something more immediate, more sensory. What would it actually look like to travel through the Milky Way? The honest answer is both more beautiful and more surprising than you might expect. Because the galaxy, as it would appear to your eyes, is largely hidden dust. The same dust grains we have been speaking of. The icy, carbon-coated, molecule-bearing grains, drifting through the molecular clouds and spiral arms, do not just sit quietly. They block light. When light from a distant star tries to travel through a region of dense dust, it is scattered, absorbed, dimmed. The dust lanes of the Milky Way hide vast regions of the galaxy from our optical eyes entirely. If you could travel to the center of the galaxy and look back at the disk from the outside, you would not see an unobstructed spiral. You would see a galaxy partially veiled, dark lanes cutting through the bright arms, regions of obscuration, hiding the stars behind them. Even from Earth, we cannot see the Galactic Center with our eyes, or with ordinary optical telescopes. The dust is simply too thick. Too much light absorbed along the way. The center of our own galaxy is invisible to human eyes, hidden behind thousands of light years of dust. And the dust lanes themselves vary dramatically from place to place across the galaxy. In some regions, the dust is so thick it blocks nearly all optical light, creating dark patches against the brighter background. The Coalsack Nebula, Barnard 68, the Great Rift, that dark lane cutting down the heart of the Milky Way, visible on a clear night as an absence of stars rather than a presence. Darkness, that is itself a structure, a feature, a thing worth looking at. In other regions, the dust thins. Windows open in the veil, allowing glimpses through to the stars beyond. The galaxy is not uniformly transparent. It is mottled, patchy, full of contrast, a landscape of obscuration, with occasional clearings, where the view extends much farther than expected. But here is the extraordinary thing. Dust blocks optical light, the light our eyes can see. But light comes in many forms, many wavelengths, many energies, and different wavelengths of light pass through dust very differently. Infrared light, with its longer wavelengths, passes more easily through dust. It slips between the grains, where optical light cannot. In infrared, the galaxy looks different. The dust lanes are less opaque. The older, cooler stars glow more prominently. The structure of the disk, and the bar at the center, becomes clearer. Radio waves, with wavelengths far longer still, pass through dust almost entirely unimpeded. In radio light, the galaxy reveals itself differently again. The cold neutral hydrogen gas, invisible to optical eyes, blazes in radio wavelengths, mapping the arms, the filaments, the vast shells, showing us a galaxy we could not otherwise see. X-rays reveal the hottest gas, the million-degree plasma of superbubbles and supernova remnants, glowing in high energy, invisible to any eye, but detectable to our instruments. Gamma rays reveal the most energetic processes, the regions near the Galactic Center, the sites of the most violent events in the galaxy's ongoing life. And so the Milky Way is not one galaxy. It is many galaxies, depending on how you look at it. Each wavelength revealing a different layer, a different population of objects, a different story. The galaxy emits light across the entire electromagnetic spectrum, from the longest radio waves to the shortest, most energetic gamma rays. Each band of light, a different voice. Each voice telling a different part of the same vast story. And when you bring them all together, when you listen to every voice at once, you begin to hear something like the full song of the Milky Way. Complex, layered, rich beyond description. A song that has been playing for 12 billion years. And you, resting quietly now, are inside it, part of it. One small, warm presence within the vast, luminous, multi-layered song of a living galaxy. Let that surround you. Let it settle over you like the softest imaginable darkness. You do not need to see every wavelength. You do not need to hear every voice. Just rest here, in the quiet, in the warmth, in the gentle, invisible radiance of everything around you. The galaxy is singing, and you are drifting peacefully through the music. Rest now. We continue whenever you are ready. And still, we drift deeper into the song, deeper into the light. That is not quite light. The radiance that only instruments can hear. Let the breath settle. Let the body grow heavier. We have been traveling through a galaxy of many voices, many wavelengths, many hidden layers. And now, we listen more carefully, because the Milky Way is not simply different in each wavelength. It is almost unrecognizable. from one band of light to the next. Invisible light. The galaxy appears as stars in dust lanes. Bright points. Dark patches. A river of faint light across a dark sky. But switch to infrared, and everything changes. The dust that blocked your view becomes less of a barrier. Older, cooler stars that barely registered before now glow warmly across the disk. The bar at the center stands out more clearly. The structure of the galaxy snaps into focus in ways that optical light never allows. And scattered across this infrared galaxy, glowing in particular bands of infrared light, are molecules with a beautiful and unusual name: polycyclic aromatic hydrocarbons. Astronomers call them PAHs. These are complex organic molecules, ring-shaped structures of carbon and hydrogen, floating through the interstellar medium, found at the surfaces of molecular clouds, found in the diffuse gas between the stars, found almost everywhere astronomers have looked. When ultraviolet light from a nearby star strikes a PAH molecule, the molecule absorbs that energy and re-emits it as infrared light, glowing, fluorescing in infrared images of the galaxy. PAHs light up the edges of molecular clouds. They trace the boundaries between dense gas and the radiation pouring from young stars. They mark the places where the harsh light of new suns meets the sheltered quiet of the clouds that gave them birth. They glow at the frontier between creation and destruction, between light and dark. And the dust itself is not static. The dust grains of the Milky Way are not all the same. They were not made the same way, and they do not stay the same. As they drift through different environments, dust grains are born in the expanding shells of dying stars, in the cool outer layers of aging red giants, in the debris of supernovae. Each source producing grains of different sizes, different compositions, different shapes. As these grains drift through the interstellar medium, they are processed, shattered by shock waves, coated by ices and cold clouds, stripped by ultraviolet radiation in exposed regions. The dust evolves across different environments of the galaxy. The grain population changes. In dense clouds, grains grow larger, coated in ice mantles. In harsh radiation fields, grains are smaller, processed and fragmented by energetic light. The dust is not a fixed feature of the galaxy. It is a living inventory, constantly being made, constantly being destroyed, constantly being transformed by the environments it passes through. And as starlight travels through regions of dust, it is not only dimmed, it is changed in a subtler way. Dust grains are not perfectly round. Many are elongated, and in the presence of magnetic fields, These elongated grains tend to align, rotating slowly, until their long axes point perpendicular to the direction of the magnetic field. And when light passes through a region of aligned dust grains, something happens to it. The light becomes polarized. Its waves, which ordinarily vibrate in all directions, begin to vibrate preferentially in one orientation. By measuring this polarization, astronomers can map the direction of the magnetic field along the line of sight. The dust becomes a compass, an enormous, diffuse, cosmic compass, spread across light years of space, revealing the invisible structure of a force that threads the entire galaxy. Magnetic fields. The Milky Way is permeated by magnetic fields, not as strong as the magnets you might handle on Earth, vastly weaker, but spread across such enormous volumes of space that their influence is profound. These fields thread through the spiral arms. They follow the large-scale structure of the galaxy, running roughly parallel to the arms, guiding the flow of charged particles, influencing where gas collapses, affecting how cosmic rays travel through the interstellar medium. The galaxy is not just a collection of stars and gas. It is a magnetized system, a vast, structured magnetic environment, invisible but ever-present, shaping the medium through which everything moves. And near the heart of the galaxy, the magnetic fields become stranger, more intense, more complex. Close to the Galactic Center, astronomers have found extraordinary structures called radiofilaments. These are long, thin threads, visible only in radio wavelengths, stretching for tens of light years, oriented perpendicular to the galactic plane, running vertically above and below the disk. They glow in radio light because of electrons spiraling along magnetic field lines, moving at nearly the speed of light, tracing the invisible magnetic architecture of the Galactic Center. No one is entirely certain how they form, or why they cluster near the center, or what drives the electrons to such tremendous energies. They are one of the many quiet mysteries hanging at the heart of the galaxy, glowing faintly in wavelengths no eye can see. And as radio waves travel through the interstellar medium, they experience something fascinating, something almost dreamlike. The medium through which they pass is not smooth. It is turbulent, patchy, full of fluctuating densities of free electrons. And as radio waves move through this turbulent medium, they are refracted, bent slightly, by patches of different density. The result is something called interstellar scintillation. Radio sources, especially distant, compact ones like pulsars, appear to twinkle, to flicker, to vary in brightness, as the irregular interstellar medium shifts and flows between us and them. just as stars twinkle in visible light. Because of turbulence in Earth's atmosphere, radio sources twinkle. Because of turbulence in the interstellar medium, the same beautiful principle, written across vastly larger scales, the galaxy itself, making distant signals shimmer. And speaking of signals, the galaxy is full of natural radio transmitters, not from civilizations, but from molecules. In certain dense, warm regions of interstellar space, conditions arise where molecules can amplify radio waves naturally, spontaneously, the way a laser amplifies light, but with radio waves instead, and with molecules instead of mirrors and crystals. These are called masers. Microwave amplification by stimulated emission of radiation. Water masers, hydroxyl masers, methanol masers. Different molecules, beaming intense, focused radio emission from the regions where they form, near newly forming stars, in the expanding shells of dying stars, in the turbulent environment near the Galactic Center. Masers blaze in radio wavelengths. Intense, precise, pinpoint sources of amplified natural radio emission. Astronomers use them as beacons, as markers of specific physical conditions, as precise reference points for measuring the distances and motions of objects across the galaxy. The galaxy is dotted with these natural lighthouses, glowing not in visible light, but in radio waves, marking the locations of birth and death, of creation and transformation. And as we try to map all of this, all the stars and dust and gas and masers and filaments, one instrument has done more than any other to reveal the galaxy as it truly is. The Gaia Space Telescope, launched by the European Space Agency, has spent years patiently measuring the positions, the distances, and the motions of billions of stars. Not thousands, not millions, billions. Each one precisely located in three-dimensional space. Each one with a measured velocity, a trajectory through the galaxy, a path that can be followed backward. To understand where that star came from, Gaia has given us a map of the galaxy, of unprecedented detail. It has revealed stellar streams, an ancient merger debris, and the subtle warping of the disk, and the precise structure of nearby star clusters, all from the quiet, patient accumulation of billions of individual measurements. It is one of the greatest cartographic achievements in the history of science. A map not of coastlines or mountain ranges, but of the positions and motions of billions of suns. And yet, even with this extraordinary map in hand, the galaxy remains full of mystery, full of hazard, full of the unexpected. Because as we travel, we must remember something. The stars are not fixed. We sometimes speak of the night sky, as if it were a permanent thing. The same constellations our ancestors saw. The same patterns. The same arrangement. But this is an illusion of timescale. Every star in the galaxy is moving, each one following its own orbit, its own path through the disk, or the halo, or the thick ancient layer beneath. They move relative to one another. From our vantage point in the solar system, the nearest stars are drifting, slowly, imperceptibly on a human timescale, but measurably, in tens of thousands of years. The constellations we recognize will be unrecognizable. Different patterns, different groupings. The sky slowly rearranging itself on timescales longer than human civilization, but short by the standards of the galaxy. And some stars are moving faster than others. High-velocity stars, flung outward by ancient interactions, passing through the disk on unusual trajectories. To an interstellar traveler, this constant motion of the stars is not just beautiful, it is a consideration. Space is vast. The distances between stars are so enormous that even moving stars pose almost no practical danger on human timescales. But on the long timescales of the galaxy, on the scales we have been contemplating tonight, the stars are anything but still. They drift. They cluster. They disperse. They approach one another and pass by and drift apart again. The galaxy is a slow dance. Every star, a partner moving through the floor, following the deep gravitational rhythms of the whole. And we, drifting through it, are part of the dance, moving with our sun on its long, slow orbit, passing through arms and clouds and bubbles, approaching some stars and leaving others behind, always in motion, always part of the turning. Let that image settle over you now. The slow dance of billions of stars, each one tracing its own long, patient arc through the dark. You are not separate from this. You are carried by it. Your sun, your planet, your body, all moving together through the turning galaxy. A slow, quiet, endless dance. Let your eyes grow heavy. Let your breath find its own slow rhythm. The stars are still moving. The masers are still glowing. The magnetic fields are still threading through the arms and the gas and the ancient dust. And you are drifting so gently, so peacefully, through the middle of it all. Rest now. We continue whenever you are ready. And still, we drift. The dance continues around us, slow and vast, and endlessly turning. You have traveled far tonight, through clouds of ice-coated dust, through glowing nebulae, through the invisible song of magnetic fields and the flickering of natural masers, shining in wavelengths no eye can see. And now, the journey takes a quieter turn. Not quieter because the galaxy is peaceful here, but quieter because we are growing still enough to notice things that pass through everything without announcement. Things that fill the galaxy and yet leave almost no trace. We begin with something invisible, something that is passing through you right now, as you rest, as you breathe, as you drift toward sleep. Cosmic rays, not rays of light, not waves, but particles, protons, atomic nuclei, electrons, moving at nearly the speed of light. The galaxy is filled with them. They stream through the interstellar medium in every direction, guided and scattered by the magnetic fields threading the galaxy. Some come from supernova remnants, the shock waves of stellar explosions, accelerating particles to tremendous energies. Some may come from regions near the Galactic Center, some from sources we do not yet fully understand. They have been traveling, perhaps for millions of years, bouncing along magnetic field lines, slowly diffusing through the galaxy. And right now, several cosmic ray particles are passing through your body, harmlessly, silently, without your awareness. The galaxy, moving through you, even as you rest. And there are other invisible influences, reaching from the galaxy into the quieter corners of our solar system, far beyond the planets, far beyond even the distant edges of the Kuiper Belt. There is thought to exist an enormous cloud of icy objects, comets, frozen wanderers, drifting in the cold and dark, at almost incomprehensible distances from the sun. This is called the Oort cloud, and it is fragile, loosely bound, gently held, as the solar system moves through the galaxy, as it bobs above and below the galactic plane, as it passes through regions of slightly different density. It experiences something called a galactic tide. Just as the moon's gravity raises tides in Earth's oceans, the combined gravitational pull of the mass of the galaxy raises a kind of tide. In the distant, delicate Oort cloud, this tidal force nudges the orbits of the outermost comets, perturbing them, sending some of them on long, slow falls inward toward the sun, the galaxy itself, reaching across light years to stir the farthest edges of our solar system. An invisible hand, gentle, vast, patient, occasionally sending a frozen wanderer on a journey toward the inner planets and drifting through the spaces between the stars. There are other wanderers, far larger than comets, but just as alone. Rogue planets, worlds without suns, planets that were formed around a star and then ejected, cast out into the interstellar dark by gravitational interactions with other planets or with passing stars. They drift now in the cold between the stars. No star to warm them, no light to illuminate their surfaces. Dark, frozen, silent, and yet they exist in surprising numbers. Some estimates suggest there may be more rogue planets drifting through the galaxy than there are stars. Whole worlds in the dark, traveling alone. There is something deeply melancholy and deeply beautiful about that image. A planet with no sun to orbit, no sky that ever sees starlight from nearby. Just the faint, distant glow of the galaxy, seen from the dark between the arms. And scattered through that same dark are the remains of stars that once shone. When a star like our sun reaches the end of its life, it does not simply go dark. It swells, brightens, then sheds its outer layers, leaving behind its core a small, dense, slowly cooling ember. A white dwarf. White dwarfs are roughly the size of the Earth, but containing roughly the mass of the Sun. A teaspoon of white dwarf material would weigh tons. They do not burn. They do not fuse. They simply cool over billions of years, slowly fading from white to yellow to orange to red, and eventually into cold, dark objects called black dwarfs. Though the universe is not yet old enough for any black dwarfs to exist, the oldest white dwarfs are still faintly glowing, still warm, still slowly, patiently cooling toward darkness. But some stellar endings are far less quiet. When a star much more massive than the Sun reaches the end of its life, the core collapse is catastrophic, violent beyond imagining. In the final moments, the core collapses almost instantaneously. In the resulting explosion, a supernova releases more energy in a few seconds than the Sun will emit in its entire 10 billion year life. For a brief time, a supernova can outshine an entire galaxy. A single dying star, blazing across the universe, visible from billions of light years away. These explosions are not rare curiosities. They happen in a galaxy like the Milky Way, roughly once or twice every century. Somewhere in the galaxy, a star explodes. Every few decades, a flash of light and energy that seeds the interstellar medium with new elements, that sends shockwaves across light years, that leaves behind something extraordinary. What remains after a supernova depends on the mass of the original star. For many massive stars, the collapsed core becomes a neutron star, an object of almost incomprehensible density. A sphere perhaps 20 kilometers across, containing more mass than the Sun. A neutron star is so dense that its matter is not made of ordinary atoms. The electrons have been forced into the protons. Everything has become neutrons, packed together as tightly as the nucleus of an atom, but across a sphere the size of a city. And many neutron stars spin rapidly, precisely, some spinning hundreds of times per second. As they spin, they beam radiation outward, like a lighthouse. And if that beam sweeps across the Earth, we detect a pulse, regular, clock-like, unwavering. These spinning, pulsing neutron stars are called pulsars. Some pulsars are so regular, so precise in their timing, that they rival the best atomic clocks on Earth, ticking away in the dark with extraordinary accuracy. But some neutron stars are something more extreme still. Magnetars. Neutron stars with magnetic fields of almost impossible strength, trillions of times stronger than the most powerful magnets we can build on Earth. Occasionally, a magnetar becomes unstable. Its crust shifts, cracks, and in an instant, it releases a flash of energy so intense that it can be detected across the entire galaxy. A magnetar flare, lasting perhaps a fraction of a second, can release more energy than the Sun emits in tens of thousands of years. Brilliant, violent, brief, a flash from the dark, and then silence again. And sometimes, gravity has an even more dramatic surprise. Occasionally, a star is not merely ejected from its birth cluster or nudged into an unusual orbit. It is flung. Hypervelocity stars, moving at millions of kilometers per hour, so fast they are no longer bound to the galaxy. The most likely cause is a close encounter with the supermassive black hole at the Galactic Center, a binary star system venturing too close. One star captured, the other hurled outward at tremendous speed. These stars streak through the galaxy, passing through the disk and out into intergalactic space, escaping the Milky Way entirely, becoming travelers between galaxies, alone, moving forever outward into the void between island universes, and in the quietest corners of the galaxy, where two dense stellar remnants orbit each other, something even more subtle is happening. When two neutron stars, or two white dwarfs, or a neutron star and a black hole, orbit one another in a tight binary system, they do not orbit in perfect silence. They send ripples through the fabric of space-time itself. Gravitational waves, tiny distortions in the geometry of space, spreading outward from the orbiting pair at the speed of light, passing through everything, unimpeded by dust or gas or distance. As the waves carry energy away, the two objects spiral closer, slowly, over millions of years, until finally, they collide, merge, in a cataclysmic instant, releasing a burst of gravitational waves, powerful enough to be detected across billions of light years. We have heard these waves. Instruments on Earth, sensitive enough to detect a change in distance, smaller than a proton, have felt the space-time ripples from merging neutron stars and black holes. The galaxy whispering to us in the language of bent space. And there is another whisper, another invisible messenger, crossing the galaxy in vast, uncountable numbers. Neutrinos, nearly massless particles, interacting with almost nothing, passing through planets and stars, as though they were not there. Every second, billions of neutrinos from the sun pass through your body, through the earth beneath you, and out the other side, without a trace. And neutrinos from more distant sources, from supernovae, from the Galactic Center, from processes we are still learning to understand, are crossing the galaxy right now, passing through everything, carrying information about the most violent events in the universe, to anyone sensitive enough to receive it. We are learning to listen to these messengers, building detectors buried deep underground or beneath polar ice, to catch the rare, faint signal of a neutrino finally interacting with ordinary matter. A message from a dying star, received in the silence of a deep mine. And finally, in the midst of all this complexity, all this violence and mystery and invisible radiation, there is a beautiful idea, a quietly hopeful one. The pulsars we spoke of, those precisely spinning neutron stars, ticking away in the dark, with extraordinary regularity. Each pulsar has its own signature, its own precise timing, its own unique rhythm. And astronomers have realized that this network of pulsars, spread across the galaxy, could serve as a kind of navigation system, a galactic GPS, by measuring the arrival times of pulses from multiple pulsars simultaneously. A spacecraft could determine its position anywhere in the galaxy with remarkable precision. The galaxy has scattered its own navigation beacons across the spiral arms. Natural, precise, patient, ticking away, whether anyone is listening or not, waiting for travelers who might one day learn to read them. There is something deeply comforting about that. The idea that the galaxy, for all its violence and mystery, has also quietly provided a way to find your place within it. A network of lighthouses in the dark between the stars, each one pulsing, steady and true. You are not lost. You are never lost. Even in the vast, spinning, exploding, radiating darkness of the galaxy, there are beacons. There are rhythms to follow. There are ways to know exactly where you are. Let that comfort settle over you now, like a warm, quiet certainty. The cosmic rays are passing through you. The neutrinos are streaming by. The gravitational waves are rippling outward. From somewhere in the dark, the pulsars are ticking. The rogue planets are drifting. The white dwarfs are cooling. And you are resting, still and warm and safe, at the center of all of it. Not separate from the galaxy. Not small in the way that diminishes, but small in the way that nestles. That fits perfectly into the vast, extraordinary, quietly pulsing whole. Let your eyes grow heavy now. Let the breath come and go. Without effort. The beacons are lit. The galaxy knows where you are. Rest now. We continue whenever you are ready. And so, we turn slowly, gently, the way a great ship turns, not with urgency, but with the quiet inevitability of something following its course. We have drifted through the outer arms, through the nurseries of stars, and the cold, dark filaments, through the invisible song of magnetic fields, and the patient ticking of pulsars, in the dark. And now, the journey takes us somewhere new, inward, toward the heart. Let the breath stay slow. Let the body stay heavy and still. Because what lies ahead is the most extraordinary region in all of the Milky Way. We are approaching the Galactic Center. Even from far away, you can feel the change. The stars grow more numerous. Not dramatically, not suddenly, but gradually. The way light increases as you approach a distant city, seen from a long, dark road, out where our sun resides. In the quiet Orion Spur, the nearest star is more than 4 light years away. A vast, dark emptiness between one sun and the next. But as we move inward, toward the great central bulge, the distances between stars begin to shrink. The stellar density rises. Stars become more numerous per cubic light year. The sky, as seen from a world in the bulge, would be blazing. Thousands of stars, brighter than anything in our own night sky. A sky never truly dark, always glowing with the combined light of ancient, crowded suns. These stars of the bulge are not all the same. They are not a single, unified population. The bulge of the Milky Way contains a mix, a layering of different stellar generations, from different eras of the galaxy's history. There are very old stars, red and cool and ancient, born in the earliest chapters of the Milky Way's formation. Stars that have been orbiting the center for 10 billion years or more. And there are younger stars too, unexpected in such an ancient region. Evidence that star formation has continued here long after the bulge was thought to be complete. The bulge is not a simple fossil. It is a complex, layered place, full of stars from many different eras, orbiting together in the dense, warm center of the galaxy. And as we move closer still, the environment changes again, more dramatically now. At the very heart of the Milky Way, within the innermost few hundred light years, there is a region unlike anything in the calmer outer disk. Astronomers call it the central molecular zone. It is dense, extraordinarily dense, with gas and dust and molecular clouds, far denser than the molecular clouds we drifted through in the spiral arms. And it is turbulent. The gas here is not quietly drifting. It is stirred, compressed, heated, moving in complex, chaotic patterns, influenced by the powerful gravity of the center, and by the energetic events happening there. Temperatures in parts of this zone are far higher than in typical molecular clouds elsewhere. The gas is warm, where it should perhaps be cold, energized, where stillness might be expected. Something is heating this gas. Something is stirring it. The Galactic Center is not a peaceful place. And yet, for all this turbulence, for all this dense gas and energy, the central molecular zone does not form stars as efficiently as you might expect. This is one of the enduring puzzles of galactic astronomy. Given how much gas exists in the central region, given how compressed and turbulent it is, there should perhaps be enormous amounts of star formation happening there. But there is not. Star formation near the Galactic Center is surprisingly inefficient. The turbulence that stirs the gas also prevents it from collapsing quietly into new stars. The same energy that compresses the clouds also disrupts them, tears apart the structures that would otherwise become stellar nurseries. It is as if the center of the galaxy is simultaneously the most promising place for star formation and the most hostile. Too much energy, too much turbulence, too much interference from forces we are still learning to understand. And yet, star formation does happen there. Just not easily. Just not abundantly. And when it does happen, it happens in remarkable ways. Deep within the central molecular zone, embedded in the dense, warm gas, there are objects called infrared bright protoclusters. These are regions where stars are forming. Right now, not fully formed, not yet revealed, still wrapped in their cocoons of gas and dust, opaque to visible light, but glowing brilliantly in infrared, warm and luminous to the instruments that can see them. Young stars in the process of igniting, clusters of new suns, struggling to be born in one of the most extreme environments in the galaxy. Each one a small miracle of creation at the very heart of the Milky Way. And above all of this, above the dense gas and the forming stars, and the ancient, crowded populations of the bulge, there is something that demands our attention. A presence. We have known it was there since we began this journey. And now, we are close enough to begin to feel it. At the very center of the Milky Way, there is a source of radio emission. Compact, precise, pinpoint, discovered decades ago, and given a name, Sagittarius, a star, written by astronomers as Sagittarius A star. For many years, its nature was debated. Something very small, something very bright in radio waves, something that did not move the way an ordinary star would move. And then, over decades of careful observation, the answer became undeniable. Sagittarius A** is a supermassive black hole. Not a stellar mass black hole. Not the remnant of a single exploded star. But something vast. Something that has been growing for billions of years. Its mass is approximately 4 million times the mass of our Sun. 4 million suns, compressed into a region smaller than our solar system. A gravitational presence so intense that stars near the Galactic Center orbited in just a few years. We have watched those stars orbit for decades. Patient astronomers tracked their paths through the crowded Galactic Center, and those orbital paths told us everything we needed to know. Only a mass of 4 million suns, concentrated in so small a space, could produce those orbits. The black hole is there. It is real. It is right at the center of everything. Most of the time, Sagittarius A** is surprisingly quiet. For something so massive, it consumes relatively little material. It is not an actively feeding monster. It is more like a sleeping giant. But not always. Periodically, Sagittarius A** produces flares, sudden brightenings, in X-ray and infrared light, lasting minutes to hours. A clump of gas falls a little too close. A disrupted asteroid or small body is torn apart by tidal forces and heated to extreme temperatures. And for a brief time, the region around the black hole blazes. These flares happen multiple times every day. Sudden pulses of energy from the heart of the galaxy. Each one a reminder that the sleeping giant is not entirely still. And above and below the galactic center, extending far out of the plane of the disk, there are structures that should not exist. Should not. And yet do. They were discovered by the Fermi Space Telescope, studying the sky in gamma rays. And they stun the astronomical community. Two enormous bubbles, extending above and below the galactic center, for 25,000 light-years in each direction. Together, they span 50,000 light-years, half the diameter of the entire galaxy. These are called the Fermi bubbles. They glow in gamma rays, in X-rays, in microwave emission. Vast, structured lobes of hot gas and energetic particles, rising like two enormous plumes from the heart of the Milky Way. What created them? Something at the galactic center. Something energetic enough to blow two bubbles the size of half a galaxy. Perhaps it was a period, millions of years ago, when Sagittarius A* was not sleeping, when it was actively feeding, consuming gas and dust at tremendous rates, and pouring energy outward in focused jets of radiation and particles. Jets that punched through the disk and inflated these two enormous structures above and below the galaxy. Or perhaps it was a period of intense star formation near the galactic center. A starburst, powerful enough to drive a galactic wind, that pushed gas and particles outward for tens of thousands of light-years. We do not yet know for certain. The Fermi bubbles are still one of the great unsolved mysteries of the Milky Way. And within the gas surrounding the galactic center, astronomers have found other echoes, other remnants of ancient violence, fossil shock fronts, sharp boundaries in the gas, thin shells of compressed material, marking the edges of ancient outbursts, places where a wave of energy passed through the medium long ago and left behind a permanent scar, like the rings in a pond. Long after the stone has sunk, the surface has stilled, but the rings remain, spreading, fading, but still there. These fossil shock fronts are the preserved memories of events that happened millions of years ago, when the galactic center was a more active and violent place, written into the structure of the gas for astronomers to read, if they know how to look. And finally, surrounding Sagittarius A* itself, packed tightly around the central black hole, there is a structure of extraordinary density, a nuclear star cluster, among the densest stellar environments known anywhere in the universe. Tens of millions of stars, packed into a region just a few light years across. Stars so close together that from within this cluster, the nearest neighbor might be only a few light weeks away. Not light years, light weeks. The sky from within the nuclear star cluster would be almost incomprehensibly bright. Stars everywhere, in every direction. No true darkness. No quiet patch of empty sky. Just stars. And more stars. And the looming, invisible presence of the great black hole at the center of everything. It is the most extraordinary address in the entire galaxy. The nuclear star cluster around Sagittarius A*, at the center of the Milky Way, in the immeasurable heaven of Laniakea. And we have arrived, after our long, slow journey, through arms and clouds and bubbles, through filaments and masers and pulsars, through the turbulent central molecular zone, and the ancient populations of the bulge. We are here, at the heart of it all. Take a long, slow breath. Feel the weight of where you are. At the center of a 4 million solar mass gravitational presence, surrounded by tens of millions of ancient stars. Above you, below you, two bubbles of energy rising 50,000 light years into the halo. It is vast. It is extraordinary. It is, somehow, deeply, quietly, peaceful. The black hole is sleeping. The stars are orbiting. The fossil shock fronts are fading at the edges of ancient outbursts. And you are resting right at the center of everything. There is nowhere further inward to go. Only outward again. Back through the arms and the dust and the cold, dark filaments. Back through the density waves and the ancient globular clusters and the stellar streams of destroyed galaxies. But that journey can wait. For now, simply rest here, at the heart of the Milky Way, held by 4 million suns worth of gravity, surrounded by the oldest stars in the galaxy. Safe, still, and home. Rest now. We continue whenever you are ready. And slowly, we begin to drift away, outward, the way you might drift from wakefulness into sleep. Not all at once, not with any sharp boundary, but gradually, imperceptibly, leaving one state behind and entering another. We carry with us the memory of the Galactic Center, the blazing nuclear star cluster, the sleeping giant of Sagittarius A star, the Fermi bubbles, rising like the breath of the galaxy itself, far above and below the plane. And now, we rise, upward through the disk, through the dust and the spiral arms, through the age gradients and the density waves, through the cold filaments, and the glowing nebulae, and out, into the halo. The halo is a different kind of place, not the crowded, creative, turbulent disk, not the blazing, ancient heart. The halo is spacious, quiet. A vast, dim, nearly empty realm surrounding the visible galaxy. On all sides, the stars here are fewer. Ancient globular clusters drift slowly through the dark. Individual old stars trace their long, looping orbits far above and below the plane. It is peaceful here, but not entirely still. Even in the crowded inner regions we have left behind, the gravitational interactions between dense stellar groups leave their mark on individual stars. When a star passes too close to a dense cluster or to a region of concentrated mass, its orbit can be altered, nudged, deflected, perturbed, sometimes gently. A small change in velocity that accumulates over millions of years into a noticeably different path. Sometimes more dramatically, a star flung onto a new trajectory that carries it far from where it began, up out of the disk, into the halo. These dynamically scattered stars are one of the reasons the halo contains the mix of populations it does. Not just ancient stars formed in the earliest galaxy, but occasional younger wanderers, tossed outward by the churning of the inner disk. The halo remembers everything that has ever happened in the galaxy below, and drifting through the halo, above and below the disk, there are clouds. Not the cold, dense molecular clouds of the spiral arms, but something different. Something that moves differently. High-velocity clouds. Enormous complexes of neutral hydrogen gas, moving through the halo at speeds that do not match the ordinary rotation of the galaxy. They are fast, anomalous, unexpected, moving at hundreds of kilometers per second relative to the disk below. Some of these clouds are thought to be gas, falling inward toward the galaxy, material raining down from the halo and beyond, feeding the disk, replenishing the raw material for future star formation. Others may be the remnants of ancient merger events, gas stripped from satellite galaxies long ago and left to drift in the halo. Still others may be gas that was once expelled from the disk by supernovae or stellar winds and is now falling back. A galactic fountain, rising in the heat of stellar explosions, cooling in the halo, and raining gently back down onto the disk from which it came. The galaxy, breathing in and out, expelling gas and drawing it back, over and over, in cycles spanning hundreds of millions of years. And from far beyond the halo, from the vast intergalactic medium, gas streams also flow. Long, diffuse filaments of gas, connecting galaxies across the cosmic web. The great structure of sheets and voids and filaments that organizes the universe on the largest scales. These cosmic filaments slowly feed the galaxy, supplying fresh hydrogen to the outer reaches of the halo, gas that will eventually, over unimaginable timescales, find its way inward, into the disk, into a molecular cloud, into a collapsing core, into a new star. The galaxy is not isolated, not self-contained. It is connected to the larger universe by these slow, invisible streams of gas, part of a vast cosmic network of matter flowing between galaxies, across billions of light years, and nearby, close enough to see with the naked eye. From the southern hemisphere of Earth, there are companions, the Magellanic Clouds, two irregular dwarf galaxies, the Large Magellanic Cloud, the Small Magellanic Cloud, visible as two detached patches of the Milky Way, hanging in the southern sky, glowing softly, separate, distinct, and yet deeply connected to our own galaxy. They are orbiting the Milky Way, slowly, on long, sweeping paths, perhaps making their first close approach to our galaxy, after traveling through intergalactic space for billions of years, and trailing behind them, like a wake behind a great ship, is an enormous stream of gas, the Magellanic Stream, a ribbon of hydrogen gas, stretching halfway around the sky, pulled from the Magellanic Clouds by the tidal force of the Milky Way, over hundreds of millions of years. This stream is one of the largest structures associated with our galaxy, a great, curving banner of gas, connecting our companions to us, slowly being drawn inward, eventually, to be absorbed, to become part of the Milky Way itself. The galaxy, still growing, still gathering, still pulling in the material of the universe to add to itself, and surrounding all of this, surrounding the disk and the halo and the Magellanic Clouds, and the high-velocity clouds and the stellar streams. There is something else, something invisible, something vast and hot and tenuous, a coronal halo, a diffuse envelope of extremely hot gas, surrounding the entire galaxy, heated to temperatures of millions of degrees, thin almost beyond imagining, but extending far beyond the visible structure of the Milky Way, perhaps for hundreds of thousands of light years. In every direction, this hot corona was expelled from the disk by the accumulated energy of countless supernovae over billions of years, rising upward and outward, like heat rising from something warm. It contains mass, perhaps as much mass as all the stars in the disk, an enormous invisible reservoir of hot, diffuse gas, enveloping everything we can see. The galaxy is larger than it appears, much larger, stretching far into the dark, in forms that only instruments can detect. And at the very edges, the structure simply fades. The outer disk grows thicker, more warped, more ragged. The spiral arms lose their definition. The gas thins. The stars become fewer. There is no sharp edge to the Milky Way. No wall. No boundary. Just a gradual, quiet dissolving of one thing into another. Galaxy becoming halo. Halo becoming corona. Corona becoming the vast, thin medium between galaxies. The Milky Way does not end. It simply becomes something else. And now, we go further still. Further than any instrument has truly taken us. Further than any probe has traveled. We imagine ourselves beyond the galaxy entirely. Looking back from out here, in the dark between galaxies, the Milky Way appears as a whole. A single object. A barred spiral. Slowly turning in the dark. And what a strange and beautiful thing to contemplate. From inside, we cannot easily see what we are part of. We see individual stars, individual clouds, individual arms. We are too close, too embedded, to see the whole. Like someone standing in a great forest, seeing only the trees immediately around them. Unable to see the shape of the forest from above. From outside, everything changes. The whole becomes visible. The spiral structure, the central bar, the faint halo extending outward, the Magellanic Clouds, hanging nearby like small attendants. But to navigate this galaxy truly, to understand the forces that govern it, we would need to account for what we cannot see. The dark matter. Navigating the Milky Way without accounting for dark matter would be like navigating an ocean without accounting for the currents. The visible surface tells only part of the story. The invisible forces beneath determine where everything actually goes. The true shape of the galaxy is not what our eyes would show us. It is the dark matter halo, vast and spherical, that determines the gravitational landscape, that sets the rotation curve, that holds the satellite galaxies in their orbits, that guided the formation of every structure we have visited tonight. The visible galaxy is an expression of the invisible one. Stars and gas tracing the contours of a dark matter scaffold. We can feel, but never quite touch. And far away, approaching, still millions of light years distant, but drawing closer. With every passing million years, is another galaxy. Andromeda, our nearest large galactic neighbor. A spiral galaxy, somewhat larger than our own. containing perhaps 1 trillion stars. Andromeda is moving toward us. Not drifting sideways. Not passing at a safe distance. But coming, more or less, directly toward the Milky Way. In approximately 4.5 billion years, the two galaxies will begin to interact. Their outer halos touching first. Then their stars beginning to mingle. And then, over hundreds of millions of years more, a collision, a merger, two great spirals, drawn together by gravity, distorted by tidal forces, their spiral arms flung outward in long, curving streams, their shapes dissolving as they pass through one another. Not once, but several times. Approaching, passing, separating, approaching again, until finally, the two galaxies settle into one. A new galaxy. Larger, rounder, perhaps an elliptical, slowly rotating in the dark. Most stars will not collide directly. The distances between individual stars are so vast that even in a galactic merger, direct stellar collisions are rare. But orbits will be disrupted. Stars will be flung into new trajectories. The night sky, from any remaining world, will be transformed beyond recognition. A spectacle lasting hundreds of millions of years. The slow, majestic collision of two island universes. And when it is over, something new will exist. Something that was neither the Milky Way nor Andromeda, but something born from both, carrying the history of both. A new galaxy, with the memories of two ancient spirals, woven into every star it contains. But that is far away, in time, and in thought. For now, let us simply rest in this view. From out here in the dark between galaxies, looking back at the Milky Way, as it turns, invisible light. It is a pale, glowing spiral, delicate, almost fragile looking, against the immensity of the void. Shift to infrared, and the older stars glow more warmly. The bar becomes more prominent. The dust lanes soften. A different galaxy revealed. Shift to radio, and the hydrogen gas blazes. The spiral arms mapped in a different language. The Magellanic Stream curving away in a great, luminous arc. Shift to X-ray, and the hot corona glows. The superbubbles and remnants, visible as bright structures in the energetic sky. And gamma ray, and those extraordinary Fermi bubbles, rise above and below, like the lobes of something breathing, something alive. Every wavelength, a different face. Every face, the same galaxy. One galaxy, many languages, many stories. All of them true. All of them ours. And here, at the end of our long journey, we hold all of it together. The cold filaments in the blazing nebulae, the ancient globular clusters and the newborn stars, the pulsars ticking in the dark, and the magnetars flashing, the rogue planets drifting alone, and the binary stars spiraling together, the Fermi bubbles rising, and the fossil shock fronts fading, the dark matter halo, invisible and immense, holding everything together in its quiet, eternal embrace. And at the center of it all, one small, warm planet, one small, warm person, resting, breathing slowly. You have traveled tonight, from the Orion Spur to the Galactic Center, from the nuclear star cluster to the edge of the halo, and out into the dark between galaxies. You have seen the galaxy in every wavelength, heard its many voices, felt the slow turning of something vast and ancient, and still, somehow, familiar, because it is home. However far we travel, however wide the view becomes, the Milky Way is home, and you are inside it, carried by it, part of its long, unfinished story. Let that be the last thought that moves through you tonight. Not the vastness, not the distances, not the violence of supernovae, or the mystery of dark matter, or the slow approach of Andromeda. Just this: you are home, inside a living galaxy, turning slowly in the immeasurable heaven of the universe, and everything is exactly as it should be. Rest now. The galaxy will keep turning while you sleep. It has been turning for 12 billion years. It knows what it is doing, and so do you. Sleep.